Hello again. In this example, we are going to solve another problem using combinational subsystems. Okay, now the problem is that we have a system that receives BCD digits, numbers, through a multi-bit signal of 5 bits. We only need 4 bits for BCD digits, but here we have 5 because the 5th bit is a parity bit. It's a bit that makes the word to have even parity. Okay, so basically it's like that. We have 5 lines. Okay, this is x4, x3, x2, x1, and x0. So these 4 bits are a BCD digit. Okay, but the most significant bit, the x4, is a parity bit. Okay, this one is an even parity bit, which makes the word to be even always. It means that, for example, if we are receiving or if we are receiving number 7 through our lines, number 7 would be 0, 1, 1, 1. Okay, together with these bits, the system sending this data will have put a 1 here to make the parity of the word even, to have 4 bits in this case. If the system sends number, for example, 12, another BCD number, that would be, for example, 9, 1, 0, 0, 1, number 9, okay? The parity is already even, so the system will have put a 0 here, okay? So the problem with that is that we take that data and we have to represent it with a 7-segment display here. But we know to be sure that the data that arrived is correct, okay? Probably because we can imagine that there is some kind of sensor somewhere that generates a 4-bit data, okay? But these data have to travel probably a long distance. Probably the sensor is in a building, in a very distant location. So to be sure that we get the correct readings, we add here a parity generator very similar to an exercise that we have done in a previous example, where we send those 4 bits together with a parity bit. Okay, so we add a parity, an even parity bit here. Okay, and this is the X we receive in our system that we want to represent. So in part A of my problem, on one side, we want just to convert the data and represent with a 7-segment display, something that we have already done in other examples. But we want to check if the data is correct, if the parity is even. If not, we want to activate the output signal E, okay? Probably because with this output signal, we can show that there's an error. Probably using, for example, we can connect it to an LED using a resistor, okay? So in case of an error, we activate that signal and we have some indication that we should not take into account the value of we have represented, okay? Because this value is not correct. Okay, so first we have to plan how to build a solution. As always with combinational subsystems, there used to be different options, okay? But okay, first, we need to detect the parity of the data. For that, we will need a parity detector. Okay, parity detector, we know that we can build one just by using exclusive OR gates. With exclusive OR gates, we build a parity detector, which is also a parity generator. In a previous example, we have used one as a parity generator, but we just want it to be a detector. You remember, it's just a matter of chaining together exclusive OR gates, okay, one and another OR gate, or simply building an exclusive or a multi-input exclusive OR gate. So simply our parity detector will be something like an exclusive OR gate with, in this case, with 5 inputs. I put value X here, and the output will be 1 when parity is odd. Okay, we'll have a, when we have a 1 here, it means the parity is odd. When we have a 0, it means the parity is even. Okay. So the error signal is activated when the parity is not correct. Because my parity bit is an even parity bit, not correct means the parity is even. So from this output, we just take our error signal. Okay? So we have solved the problem of detecting an error, because we detect when parity is odd, because it's incorrect. Now for the representation, my BCD number is in bits 0 to 3, so it's even easier to do. Let's move it over here. Okay, and so we just need a binary to 7-segment converter. So let's see. Let's move things around a little bit. It is very common when finding the solution for a problem to start with one option. Maybe we have to change afterwards. We have to delete some parts of the solution. We have to rework the solution a little bit. It's perfectly normal. It's difficult that the first version is the final correct one. Okay, so this actually reflects the usual way to solve a problem. So doing it in a very schematic way. Here we will take bits. We have 5 bits here. We have 5 bits here. The whole data X. Here we only have 4 bits. So we extract bits 3 to 0 of our signal X, which they are the bits that carry the BCD number, and this is a binary to 7-segment converter. Okay, this will give our 7-segment output here as seg. Okay, 7 segments. Okay, this one to have a final solution. Okay, this one I will connect to my 7-segment display. This one I will connect to my LID or any other indicator. Okay. Okay, so basically this solves the problem for the part A of the exercise. Now, if there's an error, we'll get a signal here. It will activate. Now, but what happens if we have an error? For example, consider that we have an input value X that is, let's check different cases. Okay, so these my 7-segment result and the error. So imagine, for example, that the input value is, as I told you before, is let's take these examples. 1 0 1 1 1. Okay, it's 1 0 1 1 1. Okay, parity is even. Okay, so it's correct, and the number is number 7. I will get a number 7 displayed in my 7 segment. Instead of putting the bits here, I just put the number that will be represented. Okay, in the other case that I have a 0 1 0 0 1. Okay, so this is parity is even, it's correct, and my number is number 9. Okay, that's great. Okay, now imagine that I get a number like this, is I get in 1 0 0 1 1. Okay, in this case this one part will be converted and it will give number 3, but in this case the parity is odd. It means that the original number, the original data generated by my system, but the system that provides the input have suffered some error during the traveling to my detector. Okay, there's been some kind of noise or something affecting the transmission, so we get an error in the input. Okay, still my converter will convert it and show number 3, but because the parity is odd in this case, we'll get a 1 here. So we are able to detect that we have an error. Because we have an error, we have to discard this value. Okay, we don't have to take into account, because probably we have an error because one bit has changed. It may happen that the original value that has been sent is like this, for example. Maybe the original value was something like this, but at some point this 1 became a 0. Okay, or maybe this 3 is correct, but the parity bit changed during transmission. Okay, so when there's an error, we have to discard the value that is displayed. But anyway, still a value is displayed in my sensor. Okay, also, what happened if I get something like this? Imagine that I have 1 1 1 0 1. Okay, okay, in this case, okay, so in this case, the parity is correct, is even. Great, but what's the number that I take here? This corresponds to number 13, actually. Okay, this represents number 13, but this is not a BCD number. Okay, so this solution is not completely correct, because we need to activate the error in these cases. Okay, in case that there's a parity error, but also in case that the number I get is not a BCD number. So it's not yet my full solution. You can see the exercise as to do. The error will be activated when the parity bit is not correct, or the input is not a BCD digit. Okay, so we have to rework it a little bit. Now, for our error output, this signal actually detects when we have an error in the parity, but not an error in the representation. Okay, so we may do a block that detects when the number is not a BCD number. Okay, but actually any number that goes from 0 to 9 is a correct BCD digit. We can detect an error in that by using a comparator. If we compare my input number, the input number is only in the least 4 significant bits. If we compare that number to number 9, if the number is greater than 9, then it's an error, because a BCD cannot be greater than 9. So we are going to delete E from here. And now we are going to consider that we also need to detect that error in the BCD representation. So basically, what we think, the way we think is if x only the part 3 to 0, I'm using Verilog notation here, okay, because so you get familiar with that. On paper we also can use something like 3 dot dot 0, something like that, okay? But when this part of the input number, the part representing the BCD digit, is greater than 9, then we have an error, okay? Or when the parity of x is odd, then we also have an error, okay? So see that, okay? We check the parity of x and check if it's odd. This is this part of the circuit. We have already done that, okay? Now, we're going to check if x is greater than 9. We do it with a comparator. You think, the idea is you think the tasks you want to do, and then you try to find the block, the standard block that do those tasks, sorry. So I have to compare x against 9. So I can use a standard comparator. I put x in the A input. From here, I will only take bits 3 to 0. So this is a 4 input comparator. In the other input, I will put number 9. Okay. You know that this representation, this is a short, a simplified representation to say that we have 4 inputs going to port B, and I put here number 9. Okay, it means I put here 1 0 0 1. Okay, and now I have the greater than, the equal than, and the less than. So when we want to detect when x is greater than 9, I put 9, so I will consider this output. This is the output that will be activated when it's greater than 9. And I want my error to be active when this signal is on, signal is 1, or when this signal is 1, the one that detects not a BCD, or the one that detects that we have a parity error. So what I will do is just to combine them with an OR gate that will make a 1 in either case. So we are using our understanding of the logic operation of the gate, and this will give my error. Okay, somehow I have deleted this part here. Okay, I don't know why. Oh, the sec here. Okay, so that's it. That's a good solution for my circuit. Okay, at least for the first part of my circuit. Okay, now let's go to the second part. The second part says, now if I have if my, as I told you before, now in this case, okay, if I have an error here, I don't really know what my 7-segment display will display. It depends on the binary to 7-segment converter. If it's only a BCD converter, it will display some strange value here, or just a dash or whatever. If this has been designed as an hexadecimal 7-segment converter, it may represent number 13. Number 13 is the letter D. Okay, so it may represent something like letter D in my 7-segment display. We don't really know, it depends on the details of the converter, but in this case now, this will be an error, okay? And we will detect that there's an error not in the parity, but in the BCD representation. Okay, now part B says that it will be very nice that in case of an error, I have it easily represented in my 7-segment display, okay? In my 7-segment display. So we will assume first that this binary to 7-segment converter, okay, this is an hexadecimal converter, which is most common. If you have to design the converter, it's very simple to design it to be hexadecimal. Okay, gives you more flexibility. It will do something like this. There's an error, and then it represents number D. So the good thing is that if we have an hexadecimal converter and we have an error, it will be very nice that in cases like this, instead of representing a D, for example, if X is equal to what we have here, 1, 1, 1, 0, 1, we would like to represent, we would like that E is equal to 1, it's not BCD, but we would like to represent it by showing an E letter in my 7-segment converter, okay? E that we can understand it's an error, E from error. And we can do that if we represent number 14, because the hexadecimal E is equivalent to number 14 in decimal, okay? This is the E in hexadecimal. So what we have to do is that when we have an error in the BCD representation, we do not only activate the error signal, but also we have to trick our converter not to convert the original number, but to convert number 14, okay? We can do that also by slightly modifying our system, okay? In this case, we modify this part, the conversion part. So the basic idea is now, if we repeat our reasoning that we did before, so now if regarding the 7-segment output, okay, what we have to do now is that if the BCD part of my input is greater than 9, okay, then what we do is that we display or we convert or we display our number 14, okay? We convert number 14, which represents the E, okay? If not, we just, okay, convert the original number, okay? And the rest is the same for the error, okay? If it's greater than 9, it's just the same. So we already have the signal that show us, that inform us that we have a number greater than 9, which is the greater than output signal of the comparator. And in this case, we will have to convert X or convert 14. It's just a problem of selection, okay? And whenever we have a problem of selection, we have to think about a multiplexer, okay? So I will select if we output or if we convert the regular number or we convert number 14. Okay, we could do it in both sides of before the binary to 7-segment converter or after the 7-segment converter, because we have actually fewer. If our 7-segment converter is actually hexadecimal, we can do it at the inputs, just exchange the original number by number 14, and it will convert it, make it an E, and that's it. Okay, if we have a binary to 7-segment converter that is not hexadecimal, we could do the selection after the converter. So in case we have an error, we can generate the 7-segment code that we want to represent. It gives us more flexibility maybe, but it's not really necessary. Okay, we can do it in two ways. So I will call this signal G to show what will be the solution. Okay, we have the binary to 7-segment converter there. I will try to make some room here. Okay, so this one option could be this one. We have our binary 7-segment, okay, converter. It works in hexadecimal mode. It converts also hexadecimal numbers. So now at the input, we'll have a multiplexer. This is a multi-channel multiplexer. It uses the 4-bit data. And depending on the result of the comparison, okay, this signal here, if it's 0, it means that the number is 9 or less. So it's not a problem, okay? So in this case, I connect the original signal, x320. But if this signal is active, it means that there's an error here. So I here put number 14, okay, represented with 4 bits. Okay, this will be converted and it will generate the right code here. This is option 1, assuming our converter is hexadecimal. This number 14 actually stands for 1110, okay? 8 plus 4 is 12 plus 2 is 14. We can also do it at the output, as I said. So the other option that is also valid, even if our converter is not an hexadecimal converter, could be to just convert the original number 320, okay, with our being to 7-segment converter. We have the conversion for the correct number, okay. We have 7 bits here, 7 bits here, and now I will select this or the other option depending on the result of the comparison. So this will be our 7-segment output, 7 bits. I will select depending on G. Okay, so in case this is not greater, it's all everything is correct. So I take the original converted number to the output. But if there's an error, okay, here I will put the code that signals the error. These are 7 bits. So it's also a multi-channel multiplexer. We are using 7 multiplexers here, while only 4 multiplexers here. So that's why this solution is better if our converter is already hexadecimal. And now here we will put the code to represent the E at the output. If you remember, in a 7-segment converter, go up, okay, this is in order this is the code is normally named with letters. This is A, B, C, D, E, F, and G, okay, in that order. So an error will activate A, F, G, E, and D. Basically, the code for letter E, for letter E, could be, this is a 1 0 0 1 1 1 1. Okay, so this is the value I have to put in this converter. Okay, this is the constant I will put in this line here. Okay, 1 0 0 1 1 1 1. Okay, so that's it. This is the solution. This could be the solution for part B, part problem. Okay. So now again, the idea is that we need to have a clear understanding of our problem. We have to detect the tasks we want to do. Okay. We have to convert. We think on the standard converters or design a specific converter if we need. Then we need to detect parity. We think of what we have learned about parity detectors. We also need to check if something is valid. In this case, we can check that only by comparing. So we use a comparator. Okay. We have to combine signals. If it's a simple combination through a basic logic operation like OR or AND, we just use a gate and combine those two options to make just one. Okay. And then sometimes we need to make a selection, and every time we want to do a selection, this is the task of the multiplexer. Okay. So and that's it. I hope you enjoyed the exercise. Thank you.